Let's add letcc to our language. I'm going to go back to the interpreter with just lambda and add letcc as a new form, where we have an identifier that we're binding in the letcc and the body expression of the letcc. Since letcc binds a value to a new kind, binds an identifier to a new kind of value, then we need a new variant of the value data type, continuation v, which has inside of it just a continuation. In interp, for the new letcc form, then we have the identifier and the body, and the way letcc works is it starts interping the body in an extended environment, where the environment is extended to bind the name to the current continuation. So k is the current continuation, and all we have to do is wrap that in cont v to make it a value, bind it, and throw that into the environment, and then we can continue by interping the body with that same continuation. So notice we've made a copy of our to-do list effectively here. Notice also that we don't have a new kind of continuation record. That's because in letcc, after we have interpreted the body of the letcc, then there's nothing more to do. That body is the result that we're looking for. The way we use a continuation value is in an application form. So we change the existing doAppK, which used to say, is it a closure, otherwise give an error, to now have an extra case. If the function that we're applying is actually a continuation, then inside of it there's a continuation that the cont v is wrapping, and then we should continue with the value that is passed to the continuation using that continuation. So notice that when we do that, we throw away next v, next k, and k. So this is the jumping effect of applying a continuation. We just continue with whatever continuation we had stored, forgetting about the rest. And that's all there is to the implementation. And I have a couple of new examples to go with that. Here is one that builds up a context where we're adding one. We bind k to the context that's just going to add 1 and invoke it inside of a bunch of pluses so that what we get out is 5 because the 4 goes to the context that does +1. That example is straightforward and it's an example of jumping out with a continuation. Here's an example of jumping in. So here I have the pattern letcc kk, which means we take the current continuation and we just return it. So the k that comes out here corresponds to let f be a bullet and f applied to lambda x 10. So that's the context that is remembered by this letcc. And that context is bound to f itself. So that when we apply f to this function lambda 10, then the whole program changes to this thing, but with a lambda x10. And now f is bound to lambda x10, so when we pass it some other function, that function is ignored as x, and the result is just 10 going out. So a little odd, but we can reason through it. Here's a more complicated example. Here I'm letting v be 1 plus some number, except I never actually produce a number. Instead I grab the continuation and throw it out through escape out to here. So the result of this gray part is going to be the continuation k that I escaped with. And that continuation is one that is binding v to 1 plus a dot. And then I apply that continuation to 2. So a 2 then goes in place of that dot, and I add 1 plus 2 to get 3. And then I return a function that takes a number and adds it to 3. So that function is the result the second time for this gray area. And so I pass 2 in for a, and I add 3 plus 2, and we'll get 5 out when we run this program. So this program shows that not only can we jump back into a computation, but we can perform some computation twice. We end up taking this 2 and adding it twice, once up here and once down here, in a very convoluted way. This is not useful yet, but it just illustrates that letcc is working the way that it should.